This is Chapter 2, Part 2, and Chapter 4, Acceleration. In this lesson, we're going to learn about the rate of change of velocity, and that's what acceleration is. And we'll learn about the different situations in which we find acceleration, especially the acceleration that's due to gravity, but not restricted to that. This is an animation just to get a better feel for what acceleration is. All right, so let's suppose we move this guy down to -10, and we're going to give him an acceleration of 2.00 meters per second squared. So what I'd like you to do is keep your eye on him first. Don't worry about the position, velocity, and acceleration sliders. Just keep your eye on him and see what he does. Here we go. All right, what did you notice about him? Well, obviously you noticed that he started from rest and then he went faster and faster. He accelerated. And he accelerated at exactly 2 meters per second squared. Now what that means is, remember that meters per second squared is the same as meters per second per second. And so what does that mean in terms of this guy? It means that each second his velocity increased by 2 meters per second. Okay, now we're going to watch the same guy and we're going to see what it looks like. This is going to be the same kind of path. The only difference is that this time you need to be looking at the sliders, the position, velocity, acceleration sliders, and see if you can notice a pattern. All right, just keep your eye on the sliders. Here we go. Okay, so what did we notice? Well, what you should have noticed is that as he was accelerating, the acceleration slider stayed still, and that's because his acceleration was constant. The velocity slider increased at a steady rate, and that's because each second that went by, there was an increase of 2 meters per second. And then you probably noticed that the position slider accelerated just as the person accelerated. Now we're going to look at the same accelerating person, and this time what we're going to do is look at the graphs of position versus time, velocity versus time, and acceleration versus time. Alright, so we're going to set his position at -10, just as we did before, and his acceleration at 2.00 meters per second squared, as we did before. And the point of this is to now see what these graphs will look like. Okay, so here we go. It's going along, about to crash into the wall, but I saved him from crashing into the wall. Anyway, let's look at the graphs. Alright, so the position versus time graph is like what we saw in the introductory slide of this video. You can see that it's a curve, and that's because the position is increasing as the square of the time. It's like a part of a parabola. And so that's why we have a curve. If you want to think about it in more qualitative terms, as time increases or as time elapses, the position increases faster and faster. That's exactly what acceleration is. Now look at the velocity versus time graph. As you would expect, it's a straight line, And the slope of this straight line is the acceleration. So if you were to look at this slope, you can look at this point right now that I'm kind of tracing over with the mouse arrow. Notice that this point that I'm tracing with the mouse arrow lines up with t equals 3, or t equals 3 seconds. Now notice that at t equals 3 seconds, the velocity has increased to 6 meters per second. And 6 meters per second divided by 3 seconds is 2 meters per second squared. And so once again we see confirmation that the slope of the velocity versus time graph is the acceleration. And let's look at it from another perspective. Let's look at the area. Well, let's see. If we look at the area under the curve at t equals 3 seconds, we would have a height of 6. We can see there's a height of 6 meters per second. We have a run of 3 seconds, and the area under this graph would be 1/2 base times height. So that would be 1/2 times 3 times 6. And so we're talking 9 meters. And sure enough, if we look at this point on the position graph, and so now I'm continuing up, notice that I'm still at t equals 3, and I'm at exactly 9 meters. Now, you might look at the graph and say, no, you're not, you're at -1. Well, but -1, considering that the starting point was -10, means that we've covered 9 meters. This is not a position versus time graph, but rather a velocity versus time graph. And the slope of a velocity versus time graph represents the acceleration. All right, because the rise is in meters per second, the run is in seconds, and meters per second over seconds gives you meters per second squared, which is the unit of acceleration. Okay, now let's look at this a little more specifically. And so we're going to call our y coordinates and our x coordinates by these names. Notice that I have, if you look at the far left, I have on the vertical axis VI and VF, and I have TI and TF. I'm just relabeling to explain this formula. Average acceleration equals delta V over delta T, and that's just difference in velocity over difference in time. And that's equal to VF minus VI over TF minus TI. In an earlier video, I told you that delta is always difference, delta difference. They both begin with D. But when you're doing deltas, always remember that it's final minus initial, not the other way around. It's final minus initial. Now let's look at that in terms of this graph. Okay, let's look at the rise first. We have VF minus VI, and that would give this portion that I'm tracing now with the mouse arrow. That portion would be the rise of this particular segment. And then the run would be TF minus TI. And that would give us this portion that I'm tracing now with the mouse arrow. That would be the run. Okay, so I got rise over run, and that will give me the slope, which is the same as the average acceleration between these 2 points. Okay, so this is just a quick way to visualize a definition. This is the definition of average acceleration, which is delta V over delta T. Okay, now bringing that forward, we have average acceleration equals delta V over delta T equals VF minus VI over TF minus TI. Now, when acceleration is constant, this becomes something else. Okay, now what do I mean by acceleration is constant? I'm just going to backtrack really fast. What acceleration is constant means is that instead of a curved green line, you just have a straight green line. That's a constant acceleration. Okay, because it's a constant slope when you have a straight line. Okay, so when acceleration is constant, this definition becomes A, just acceleration. You don't have to call it average because it's the same acceleration along every point of the line, equals VF minus VI over T. Notice all we did is we did some algebra on the original definition at top to arrive to this step, and you can think of it as just multiplying both sides by T. Why did TF minus TI just become T? Because we're dealing with elapsed time, and since TI is simply 0, we're just calling it T, and it's simpler to work with that way. All right, so we have A equals VF minus VI over T, and that gives us VF equals VI plus AT. This, whenever you see an equation in this class, and in the videos you see, you'll see some intermediate steps because I like to try to derive some of the equations, but the final equation will always be framed in a box, okay? And that's going to help you in your notes because you can highlight that, and then when you're referring to your notes, you won't be confused by the derivations. You'll just go straight to the actual equations that you need. So this is the first one. VF, or the final velocity, equals VI, or the initial velocity, plus the acceleration times the time. And again, this formula really just comes from the definition of average acceleration that we started with. Now let's look at this velocity versus time graph. All right, in this velocity versus time graph, we can see that there's a straight line. And if there's a straight diagonal line, you know, of course, already that the slope represents the acceleration. That's nothing new. And we know that it's constant acceleration because the slope is the same throughout. Slope never changes. All right, and we also know from the earlier stuff we've done that the area under this line, or the area under this graph, is or represents the displacement, the S. S is the symbol for displacement. All right, so the area is displacement and the slope is acceleration. Okay, so what does this mean? Well, here's one thing it means. And notice that I highlighted already because this is actually an important equation. It's one of the 5 that we're learning today. But there's no complicated derivation because we can see from the graph why it's true. All right, if we look at this, for example, well, I've indicated the VAV with this dotted line. You can see that it goes right through the midpoint, of the red line. And the part of the red line that we're focusing on, of course, is the part above the shaded area. Well, the midpoint of that portion is represented by VF. And that's simply the numerical average, because if you add VF and add it to VI, VI is 0, well, that just gives you VF. And you know, when you're doing the average of two things, you just add them up and divide by 2. And so VF plus VI divided by 2 gives us the average velocity. Okay, so this dotted line is the VF. We get that, or calculate that average by adding VF, that I'm tracing now with the mouse arrow, VF, to VI. Notice that VI is just 0. And then dividing that sum by 2. That's to get the average, and therefore we can clearly see that average velocity equals 1/2 VI plus VF. Now here, for the sake of simplicity, I've made the VI 0, but there will be times when the VI isn't 0. For example, let's say you're on the road, you're driving at a constant speed of, I don't know, 70 miles per hour. You're on the freeway. Constant speed is 70 miles per hour, 70 miles per hour. You're going along, and then suddenly you want to change lanes. So you accelerate to 80, change lanes, and then go back to 70. Well, you can tell that your initial velocity there was 70, then you accelerated. Okay, so my point is that VI is not always 0. I just made it 0 here to make the proof easier for us to understand. Now, S, or the displacement. We already know that the displacement is represented by the area under the graph. Okay, so this whole shaded area here, if you calculate that area, you've got displacement, which is how far the accelerating object traveled in time t. And let's remember the formula for the area of a triangle. We can see here that the shaded region is the triangle, and so we're going to do 1/2 base times height. Well, my base is t. My height is VF plus VI. VI just happens to be 0, and so that's easy. And notice now, if you do 1/2 times base times height, you end up with this formula that I'm circling now with the mouse arrow, the third of the 5 important equations that we need to learn today. S, or the displacement, equals 1/2 VI plus VFT. Now, there's another interesting way to think of this. Look at the first one that I showed you, 1/2 VI plus VF. All right, well, if that's my average velocity, if you multiply that by t, you've got the displacement. Well, look at it in terms of area. Let's suppose that instead of accelerating, we just went from rest, and we went at VF, we just kept VF, never accelerated, but maintained a constant velocity of VF during the whole trip that took time t. Well, if you look at that area, and again, I'm talking about the area underneath the dotted line, because now I'm talking about a different graph, because now we're talking about something that has constant velocity. Well, if you look at the area underneath the dotted line, we're talking about a rectangle. And the area of a rectangle is just base times height, or width times length. Well, my length is t, My width, or my height, is VAV. T times VAV will give me area. And notice that this second equation here is simply T times VAV. Okay, so it's neat to see how it all comes together. Motion with constant acceleration. We're going to continue to derive our equations. We're going to derive two more. And then you will have completed your 5. And these are the 5 that you really need to learn and memorize because they will come up over and over again during this course. All right, so let's take these two equations and put them together. All right, we took the third equation, s equals 1/2 vi plus vft, and we took the first equation, vf equals vi plus at. Notice what we did here. We simply plugged the vi plus at in for vf, since it equals vf. We're using substitution here. And now we can simplify, rewrite it as s equals 1/2 times 2vi plus at times t. And then doing some more algebra on that, we end up with s equals vit plus 1/2 at squared. This is the fourth of the 5 equations you need to know for constant acceleration. S equals vit plus 1/2 at squared. Now let's just carry these 4 forward since we've proven them already. And let's prove our fifth and final equation. Okay, this time we're going to use the first one. And if we use the first one, notice that we can rewrite it, isolate t, and write t in terms of everything else, and we get t equals vf minus vi over a. Then we take the third one, and instead of writing t, this time we're writing vf minus vi over a, since that's equal to t. Notice how I just plugged it in here. And then we have s equals 1/2 times vi plus vf times vf minus vi over a. Now, doing some algebra on that, we end up with s equals 1/2 vf squared minus vi squared over a. If you don't readily see that, you should do the steps because it's always good to brush up on your algebra. You should be able to do the algebra that gets you from this step to this step. And I would say don't continue the video until you can actually do that yourself algebraically. You'll see that it comes out because vf minus vi times vf plus vi is a difference of squares. Okay, and so we have s equals 1/2 times vf squared minus vi squared over a. And then rewriting that, we have vf squared equals vi squared plus 2as. And that again is just doing some more algebra. All right, remember, a quick note on derivations. I put derivations whenever possible, whenever we can, because it's much better to see where equations come from instead of mindlessly memorizing them. Okay, now once you do see where an equation comes from, you need to memorize them, but then that's what I would call mindfully memorizing. It's not the same as mindlessly memorizing, because you have actually seen where the stuff comes from. So basically, the bottom line is learn the 5 equations, know them, memorize them. You'll be using them all year. The derivations, you can refer to them when you need to. You don't have to memorize the derivations. You certainly don't. If you have questions on any derivation, you're certainly welcome to ask me in class, and I'll be more than happy to walk you through the steps. But we have now covered the 5 basic equations. They've all been highlighted with rectangles, and so make sure you highlight them as well in your notes. Okay, this is our first problem dealing with an object moving at constant acceleration. Okay, so since this is the first problem, I'd rather just walk you through it. You'll have a chance to do some others on your own. But let's just go through this together because it's very important for you to learn how to do problems like this. All right, if you just hack away at it without any system, you're probably not going to get the right answer. You have to have a strategy, and here's the strategy. First, you do a sketch. Second, you write down what you're given and what you're trying to find. And third, you decide what equation you're going to use. All the steps after that are just really plugging and chugging. Once you've identified the equation, you just plug in what you know and find what you don't know. But the first three steps are the sketch, the layout of knowns and unknowns, and the identification of which equation you need. So let's walk through those steps right now. First, the sketch. We are given some information, and obviously you don't have to draw a nice car, but you should draw something, even if you want to just draw a box. That's all right. This isn't an art contest. We're just making sure that we sketch in order to visualize the problem. Now, it's always a good idea to draw vectors and label them. Here I have the first speed vector, which is 80 kilometers an hour in green. And notice when we're at the finishing point here, the green vector is 110 kilometers per hour. And notice that the green vector to the right is longer than the green vector to the left. That's simply to represent that it's a greater magnitude. And we have our blue vector representing the acceleration of 1.6 meters per second squared. Okay, so that was step one, the sketch. Now step two. This is where you write down your knowns and you write down your unknown, or the question mark for what you're trying to find. Now, sometimes you may have two unknowns, but a good way to approach that is just do one unknown at a time. Okay? In this particular problem, we're only asked for one thing, and so we only have one unknown, and so it's easier. But we know the VF, and so we write it 110 kilometers per hour. We know the VI, and so we write it 80 kilometers per hour. We know the A, the acceleration, is 1.6 meters per second squared, and T is a question mark because that's what we need to find. All right, so we've done step one, the sketch. We've done step two, the layout of knowns and unknowns, and step three is you identify which equation you need. Now this is, for most students, especially those starting in physics, this is the trickiest step. But if you've done steps one and two well, then step three is going to be a lot easier. What you do is you look at the 5 equations that we just learned, and you see which of those equations will allow you to put in all your knowns so that you only have one unknown. Now, there are times, as we'll see, when you can use more than one equation. You'll get the same answer with each one, but normally you can just identify which one you like and pick that. So what equation are we going to use? We're going to use this one, VF equals VI plus AT. Why that one? Because we know VF, we know VI, we know A, and that leaves T as the only thing we need to find. All right, so this is the equation of those 5 equations that we're going to use. Now, once you've done that, the rest is really just calculation. So first you convert 80 kilometers an hour and 110 kilometers per hour to meters per second. And so we lay out the fractions, the best way to do unit conversions. And we end up with 22.2222 meters per second. Now you might ask, well, what about significant digits? Well, with significant digits, remember, you're rounding off at the end. When you get to your final answer, it's not a good idea to round off in the intermediate steps because that will introduce error into your answer. All right, so yes, I know if all we were trying to do was convert and do nothing more, the answer for this first unit conversion would be 22 meters per second. But we're leaving it unrounded for now, since this isn't our final answer. Converting 110 kilometers per hour to meters per second, we have 30.55556 meters per second. We already know that we're using VF equals VI plus AT. And now we just what I like to call plug and chug. Plugging and chugging means you plug things in and you chug through the calculation, and you end up with T equals 5.2 seconds. So the car took 5.2 seconds to accelerate from 80 kilometers per hour to 110 kilometers per hour. Here's another problem. A world-class sprinter can burst out of the blocks to essentially top speed of about 11.5 meters per second in the first 15.0 meters of the race. What is the average acceleration of this sprinter, and how long does it take him to reach that speed? All right, what I'd like you to do now, you're not going to solve the whole problem, but I would like you to pause the video and do the first 3 steps that I'm recommending, the sketch, the layout, and the identification of which equation you're going to use. Do those 3 steps and then resume when you have those done. Okay, so the sketch, obviously you didn't have to draw an actual runner. You could have done stick figures or whatever. But these are the basic elements of the sketch. You've got the starting point, and of course, you know, when you have 0 meters per second, really there is no vector because it's 0 magnitude. But it's a good idea to just draw a tiny little vector as a marker to help you visualize. And that's why I have this tiny little green vector with 0 meters per second, even though, as you know, technically there is 0 magnitude, so there would actually be no arrow. It's just a visualization aid. Then here on the left, after he's accelerated for 15.0 meters, his speed is 11.5 meters per second, and you can see the magnitude of the green vector is larger because his speed is increased. So that's the sketch part. The layout, VF, we know, 11.5 meters per second. We also know VI, and we know S, the displacement. So we're trying to find A. And finally, the identification of the equation. Well, we choose this one because it allows us to plug in our knowns and have only one unknown. So VF squared equals VI squared plus 2AS. Okay, now if you're up for the challenge, you can pause the video and then solve. If you don't feel up for the challenge yet, just watch the rest of this solution. All right, so we have VF squared equals VI squared plus 2AS. Now we can rearrange terms to leave A by itself, since that's what we're trying to find. And we have A equals VF squared minus VI squared over 2S. Then we plug and chug and come out with A equals 4.408 meters per second squared, which is rounded to 4.41 meters per second squared. Now let's find the time. Okay, so this is an example, this problem is an example, when there are two things you need to find. First we need to find the acceleration, and then we need to find the time. You don't have to freak out when you're asked for two things that you don't know. You just do your solution in two basic steps, or two main parts. Okay, part one, or phase one, is going to be finding one of the things you're asked for, and then phase two will be finding the other thing that you're asked for. So we were asked to find the time. We've already found the acceleration, and we're going to use VF equals VI plus AT. And that's because we know his VF, we know his VI, we found his A, and so we just need to find T. We do our plugging and chugging, and we end up with 2.61 seconds as the amount of time it took him to accelerate from rest to 11.5 meters per second. All right, now to find the time, you could have also used S equals VIT plus 1/2 AT squared. Now, how do we know that we can use this? Because, well, just follow what I'm doing with the mouse arrow now. Okay, I'm circling kind of over and over this equation, S equals VIT plus 1/2 AT squared. We know our S because our S was given, and that's 15.0 meters. We know our VI, which is simply 0, and then that's going to make this whole term 0. We know our A because we found it, and we're looking for our T. And so this is an alternate way to find the time. And you can prove this to yourself on your own. You'll end up with exactly the same T as you found using VF equals VI plus AT. All right, so my point is there isn't always just one way to do a problem. Sometimes there are, you know, 2 or even 3 ways, but you just pick one that you like and you go with it. Okay, so there is a certain amount of freedom, I guess, in physics, but there are certain guidelines that you can stay within, and these guidelines, if you follow them, will keep you from going wrong. All right, a car speeds up uniformly from rest to a speed of 21 meters per second in 6.0 seconds. How far did it travel in that time? Okay, now what you should do is, what I'd like you to do is pause the video, do the whole thing on your own, and resume when you have your final answer. But remember, follow the 3 steps before you do your plugging and chugging. All right, so first we sketch, and we've got 0 meters per second as our starting velocity, or our VI. Again, I used a little green vector just as a place marker or a visualization aid. And then we have 21 meters per second as our final velocity, and of course I used a bigger vector there. Now we do our layout of knowns and unknowns, VF and VI and T we know, S we're trying to find, and so the best equation to use is S equals 1/2 VI plus VFT. Then we do our plugging and chugging, and we end up with 63 meters. And so the car traveled 63 meters in the 6 seconds that it took to accelerate from rest to 21 meters per second. Free-falling objects. Objects falling in a vacuum fall at the same speed regardless of mass. Now, this is one of those mind-blowing realities that is a little bit hard to accept at first, but it's true. It's simply true. And later on, when we get to chapter 5, we'll get into, you'll be able to see a mathematical proof of this. But for now, you just need to accept it. Mass doesn't matter when you're talking about falling objects. You guys know that Galileo proved this, and you've probably heard this before, or you've maybe had someone ask you the question, what falls faster in a vacuum, an apple or a feather, or maybe they asked you what falls faster on the moon, where there is negligible air or negligible friction because there's really no atmosphere there. And you've probably been asked the question and you either answered wrong, or you heard the right answer, or you guessed the right answer but didn't know exactly why. Well, it's one of those things that that physics teaches us, and that we just need to accept at first, because later on when we see in chapter 5, when we learn about gravity, we'll see why this is true. Okay, so for now, just accept the fact that objects falling in a vacuum fall at the same speed regardless of mass. Obviously, the apple is a lot heavier than the feather, and yet in this high-speed photo that's taken at several hundred frames per second, we can see that in this particular photo, the apple is always lined up with the feather. Now you might ask, well, if I drop an apple and a feather together while I am at home, why does the apple fall so much faster? And the answer to that is because the air catches the feather a lot more than it does the apple, and so shape does influence free fall when you're dealing with atmosphere or air. But if you're in a vacuum and there is no air to slow down a fall, then mass is simply irrelevant. Things fall at the same rate. Now, freely falling objects accelerate at a rate of negative 9.81 meters per second squared. This is a constant. It's a constant that you need to memorize. This constant is for Earth, obviously. If you go to a different planet, or if you go to the moon, there's a different rate of acceleration, and that again has to do with gravity, as we'll learn in chapter 5. But on Earth, the rate of acceleration for freely falling objects is negative 9.81 meters per second squared. Now, why the negative, you may ask? Because the acceleration is going downward. An upward acceleration is positive. A downward acceleration is negative. Now, let's take a look at this diagram, which kind of shows altogether t, v, and x, or time, velocity, and position. Okay, so if this ball is being held at time 0, obviously its velocity is 0 and its position is 0. Then, at time 1 second, the velocity has increased to 9.81 meters per second. And this would be, of course, a negative velocity. For simplicity's sake, I'm just showing it as a positive here. Okay, but technically it's a negative because it's going down. The position I'm also showing as positive, but technically it's negative because the position's going down. That would be 4.91 meters. Now, let's look at a couple things here. First of all, we know that meters per second is the same as meters per second squared. And notice that as each second goes by, the velocity goes up by the same amount. And so for each second, the velocity goes up the same number of meters per second. All right, so from 0 to 1, the velocity goes up 9.81. And then from 1 to 2, the velocity then increases again by 9.81. You can do that addition and see that is true. And then from time 2 to time 3, the velocity increases by 9.81 again. And then from time 3 to time 4, the velocity increases by 9.81 meters per second again. And so we can see that that's a linear progression, and the slope of the VT graph is always the acceleration. So that would be a straight diagonal line on the V versus T graph. And then if we look at over here the position, we can see, well, after 1 second it's gone 4.91 meters. But then after 2 seconds it's gone a lot farther, 19.6 meters. And then after 3 seconds it's gone much farther still, 44.1 meters. And then at t equals 4 seconds it's gone 78.5 meters. So you can see that the position is increasing exponentially. It's increasing, it's varying as the square of the time. And we saw that in the very first graph of this lesson of how we have a curve for the position versus time graph rather than a straight line, because this is an accelerating object. Free fall is the motion of an object subject only to the influence of gravity. The acceleration due to gravity is a constant g. All right, so we're going to see g throughout the whole year. Think of g as simply the absolute value of gravitational acceleration. All right, so if gravitational acceleration on Earth is negative 9.81 meters per second squared, well, then g is just the absolute value of that, which is 9.81 meters per second squared. Now, an interesting thing about this table is we can see here that not everywhere on Earth is g 9.81. In fact, it varies according to latitude. And if you're curious about this, well, it's because the Earth is slightly squashed. And what that means is that the surface at the equator is a little bit farther away from the center of the Earth than is the surface at the North Pole, for example, or in Norway. And that's because of the shape of our planet. It's not a perfect sphere. And so that leads to different values of g. Now, practically for us, that means that we are going to weigh a little more if we go far north, and we're going to weigh a little less if we go closer to the equator. So I guess you could say that you could come up with some kind of crazy diet plan. You know, if you want to lose weight, just move to Ecuador. But that's not exactly practical. The bottom line is, though, you're going to weigh less at the equator than you will at the North Pole because of the shape of the Earth. Now, for our purposes, we're just always going to use a g of 9.81 because we can't be, changing g for every single part of the globe. That's going to be way too complicated. We're just going to be using a g of 9.81 the entire year. Let's suppose we have a cannon and it's going to shoot a tank shell. Well, this animation is to demonstrate some concepts, basic concepts of free fall. We're going to just be using 90 degrees for now, and later on in the video we'll use different angles. Okay, so let's fire the tank shell. We notice that we have an initial speed, which, as you know, is going to be straight up vertical, of 18 meters per second. The angle is 90 degrees, mass 150 kilograms. And let's take a look at what happens. Straight up, reaches a peak, straight down. Now notice that as it's going up, it's slowing down the entire time. And then as it's coming down, it's speeding up the entire time. Let's see it one more time. Slowing down, reaches a peak, speeding up. Now, what's important about that? What's important is that during the entire trajectory, the tank shell is accelerating downward. Now, it's sometimes hard to think of acceleration when it's slowing down. But remember that acceleration just means change in velocity over change in time. And so by accelerating downward, I mean that as the tank shell goes up, it's slowing down because it's decelerating, but that is the same as accelerating downward. You could call it a negative acceleration. And then when the tank shell goes down, it is increasing in speed, but it's still accelerating downward, simply because it's a negative acceleration. Negative because it's going down into the ground as opposed to up away from the ground. Okay, let's take one more look at it. Up, slows down, reaches a peak, speeds up, hits the ground. Okay, now another thing to point out about how gravity affects falling objects is that the mass doesn't matter. The only thing that determines how long something that goes straight up in the air stays in the air, the only thing that determines that is the initial speed. Okay, so let's do it again now, looking at these parameters, and we're going to change the mass. Now, I'm going to fire one more time with the initial speed of 18 meters per second and 150 kilograms. And let's see how high it goes. You're going to keep your eyes on the height. You'll keep your eyes on the height. And let's look for the highest value the height reaches. So here we go. 16.4. All right, and then it goes down. But at its peak, it was 16.4. Let's look at it one more time. Notice at the top, 16.41. Okay, so it is obvious that when we have 18 meters per second for this tank shell when it goes up, it's reaching a peak height of 16.4 meters. Well, let's try to change the mass. We're going to change it to 300 kilograms, so twice the mass. And do you think that the projectile is going to go higher or lower? All right, think about that and let's see what happens. Fire, peak height of 16.41. And you're thinking, what? It's twice as heavy. How can it go to the same peak height? It's going up to 16.41, just like the projectile of 150 kilograms did. Well, this is the whole point, is that gravity affects all objects in the same way, whether heavy or light. And keep in mind that we're neglecting air resistance here. That's why this box is not checked. So we're talking about ideal conditions, no air resistance. But all that matters is the gravitational acceleration. The mass does not matter. For any falling object, the mass does not affect the rate of fall. Okay, now let's see what does affect how long this airborne projectile stays in the air. Notice how we had an initial speed of 18 meters per second. I'm going to put the mass back to where it was, which was 150 kilograms. But now look where the mouse arrow is. I'm going to be changing the initial speed to only 10 meters per second. Okay, now what do you think? Is the tank shell going to go higher or lower than it did with an initial speed of 18 meters per second? Let's see. Oh, way lower. See that? Let's look at it again. Way lower. And that's because the only thing that affects hang time, if you will, or the time that a projectile spends in the air, the only thing that affects that is the initial speed. The mass has nothing to do with it. If a tennis player tosses a ball straight upward at 5.0 meters per second, what will be its peak height? If she catches the ball at exactly the same height from which it was released, how long will it be airborne? Now, since this is our first free fall problem, I think it's a good idea to just watch the walkthrough. You'll have a chance to try some stuff on your own, but just watch the walkthrough. All right, so I'm going to go through the 3 steps in our strategy, and then after that, as you know, it's just going to be plugging and chugging. Okay, so the sketch. We have the tennis player tossing the ball up just before a serve. The initial velocity, or VI, is 5.0 meters per second straight up. Notice that the acceleration opposes that upward velocity. we have a negative acceleration, negative 9.81 meters per second squared, because that's a downward acceleration, and that's opposing the initial upward velocity. And what that means is the thing is going to be slowing down as it goes up, then it'll reach its peak, and then it will speed up on its way down. Alright, so that was step one, the sketch. Step two, the layout. We know that VF is 0 meters per second. How do we know that? Because if you throw something up, well, it reaches a point where it comes to rest before it falls back down. And so its final velocity, since we're looking for the peak height, we really only care about the first half of the trip. That is, the trip from her hand to the peak. We don't need to worry about the second half of the trip, which is the trip from the peak back to her hand. And you can just, normally what you do, what tennis players do is they'll toss it up and serve it. But occasionally you've seen tennis players, and this does happen once in a while, throw it up, decide that they don't want to go for that toss, and then they just catch it again. There's nothing wrong with doing that in tennis. So let's just pretend that this server is going to toss it up and catch it in exactly the same spot where it left her hand. Okay, so we have our VF of 0 meters per second, we have our VI of 5.0 meters per second, we have our acceleration of negative 9.81 meters per second squared, and we need our S. And so step 3, we can see that the best equation to use is VF squared equals VI squared plus 2AS. And once again, just as a reminder, we're only dealing with the first half of this up and down trip. We're only dealing with the up portion. Alright, now at this point you should be able to plug and chug on your own. So do that until you have your final answer and then resume when you have it. Okay, so we know that is VF squared equals VI squared plus 2AS. So we have 0, which is my final velocity at the top of the path. 5.0 is my initial velocity, and then I just plug in the negative 9.81 for A, and I find that S is 1.3 meters. Now let's find the time airborne for the first half of the ball's trip. This is often a good thing to do when you're dealing with free fall problems, because what you're going to do is, if you're neglecting air resistance, you automatically know that the time it takes for the ball to go up and reach its peak is exactly the time it takes for the ball to come back from its peak to where it started. So we have VF equals VI plus AT. We're looking for the T. We know that the VF at the top of the path is 0 because it comes to rest. Initial is 5.0 meters per second, and we plug in the negative 9.81 to find that T equals 0.5097 seconds. Remember, unrounded until the end, because then what you have to do is multiply that by 2 to get 1.0 seconds. Why multiply by 2? Because the time it takes for the ball to go from her hand to the peak is exactly the time it takes for the ball to return from the peak to her hand. So you just multiply the ascent time by 2. Now, we could have also found the time airborne for the ball's whole trip, like this. Okay, we could have looked at that the entire trip from the point of view of displacement. Now, keep in mind what displacement is. Displacement is just where you end up in relation to where you started. So if this whole trip is considered as starting at her hand, going up, reaching the peak, and then coming back to her hand, that, as you know by now, is a displacement of 0, because it comes right back to where it started. And so if we use this method, we put in 0 for our S, our displacement. We still have the same VI, 5.0, and we're putting in negative 9.81 because the acceleration is directed downward for the entire trip. Then we simplify, and then we use the quadratic formula. This is something you learned in Algebra 1 and have seen in every math since then. Remember that you do need a lot of math for this physics course. You don't need calculus yet for the problems we do, but you definitely need to have a solid handle on algebra and trig. So if you need to brush up on your math skills, make sure you do that as part of studying for this course. All right, so then what you do is you're plugging and chugging, and then you end up with t equals 1.0 seconds. As you can see, that's exactly the t we found with the other method. You almost certainly like the other method better because it's simpler, but the point is, just so that you can learn more about physics, there are always different ways to look at a problem, and there are sometimes more than one way to solve a problem. And so that's what we see here. We see an alternate way that happens to be more complicated, but it still gives the same exact answer. All right, let's look at this problem. If I drop an egg from the roof of a building that is 90 meters tall, how long will it take to hit the ground? With what velocity will it hit the ground? Okay, so if you're ready for a challenge, you should pause the video, try to do this whole thing on your own, then resume when you have an answer. If you're not ready for that challenge yet, then just watch the solution. All right, so here we have our nice, beautiful Easter egg. Of course, you would not have to do that in your sketch. You could probably just use a circle. And then we have our vectors drawn and labeled. Acceleration vector of negative 9.81 meters per second squared. Initial velocity, since we're dropping it from rest at the top of a building, that initial velocity is 0 meters per second. And the displacement for this trip down to the ground, where the egg is going to come to a splat. That's 90 meters. Second step, the layout. We know that VI is 0 meters per second because it starts at rest. We know that our A acceleration is negative 9.81 meters per second squared. Our S, the displacement, is 90 meters, and we need time. And so the third step, we identify that we're going to use this equation, S equals VIT plus 1/2 AT squared. All right, so going through the plugging and chugging, we put our knowns in. Notice that I used negative 90. Why negative 90? Because we're dealing with a drop. All right, if you're dealing with a drop, you have a negative displacement. If you're dealing with a rise, you have a positive displacement. This is something that's important to get used to already. And now when we solve for t, we have 4.3 seconds. That's how long it takes the egg to drop to the ground. Now let's find the final velocity, since we were also asked that. Notice what we've done. Whenever you're asked for two different unknown quantities, just attack one of them first and then the other. Often, the first question that's asked will be the one you want to attack first. Then you do the second. That's not always the case, but at least for now, since we're just getting used to this, that's going to be the case. So we're going to find the final velocity. VF equals VI plus AT is the way to do that. Why? Because we know the VI, and we know the A, and we found the T, so we can just get VF as our only unknown there. Then doing our plugging and chugging, we end up with negative 42 meters per second. All that means, of course, is that the velocity vector is pointing down into the ground. That's why it's negative. Okay, let's have a little bit of fun with projectile motion. And this time we're going to see how velocity, when it's broken up into vertical and horizontal components, affects the flight path. All right, so we're going to start with a tank shell. Its initial speed is 18 meters per second, mass 150 kilograms, and launch angle is 80 degrees. So fire, you see it go up and down. All right, now a few things to point out. Notice that it goes both up and over. All right, so there we can see that there's a vertical portion of the path and there's also a horizontal portion. Well, the vertical portion of the path is due only to the vertical component of the velocity. And the horizontal component of the path is due only to the horizontal component of the velocity. All right, so like if we went right back to 90 degrees, like we did before, it goes straight up and it comes straight down because all of the initial velocity is vertical and none of the initial velocity is horizontal. Whereas if we do something with, let's say, 30 degrees, well, then we have, as you can see, a whole lot of horizontal component, but not much vertical component. See how this path wasn't so high? It wasn't nearly as high as when the angle was 90 degrees because the vertical component of the velocity is small, whereas the horizontal component of the velocity is big. And hence, the vertical component of the path is small, and the horizontal component of the path is large. Okay, let's see if we can hit the target. We had 80 the first time. And we fell a little short. Let's try 75, and we'll hit fire. See what happens. Goes up and score. Whoa, right in the bullseye. So what we can see is that the angle of the launch also affects the range, precisely because it affects the horizontal component of the velocity. Now, two things to remember with two-dimensional projectile motion. Okay, so the height is determined by the vertical component of the velocity, but the range, or how far it goes, is determined by both the horizontal component of the velocity and how much time it spends in the air. So what we have to keep in mind, especially when we're dealing with two-dimensional projectile motion, is the fact that the horizontal motion and the vertical motion are completely independent. Okay, let's go back really quickly to the 90-degree angle. Let me explain a little bit more what I mean. All right, so if I fire, again, as you can expect, there's only going to be a vertical component. But when I fire, the whole time the tank shell is in the air, it's being accelerated downward. Now, by the same token, if I change the angle, let's say to 60 degrees, again, the whole time it's in the air, it's being accelerated downward, straight downward. Now, the result is we have something that looks like a curved path because at first it's going up, it's slowing down, and then as it's coming down, it's speeding up, but it's still going to the right, and so it's tracing out a curved path. But the main thing to remember is that the horizontal component of the velocity is completely independent from the vertical component. In other words, if I, all right, let's say that I dropped something. I'm going to change the degrees now, and you'll see why in a second. All right, so notice now that I have an angle of 0 and a height of 0, and look at what happens. Okay, it drops to a height of negative 1.2 meters. I'm circling that up top with the mouse arrow now, negative 1.2 meters. Now notice that it came straight out of the barrel, but then it dropped. Okay, so and that took 0.5 seconds. Now the thing that you have to really drill into your head is that if I had dropped the tank shell without any horizontal component, simply dropped it, it would have taken 0.5 seconds to fall to the ground. Okay, so if you look, for instance, where the mouse arrow is now, I'm tracing it from the middle of the cannon to the ground, right, along that wheel there. Okay, well, what I just said is that path, if I simply dropped the tank shell, it would take 0.5 seconds to drop vertically down. That's the same amount of time it took for the tank shell to fall vertically down when it had horizontal velocity. Okay, so that's a little bit hard to accept, but it's just a fact. It's the way that physics is. Horizontal velocity is completely independent of vertical velocity, and horizontal acceleration is completely independent of vertical acceleration. All right, we're almost done with this. Let's have a little bit more fun, and let's go back to our 75 since that was a winning angle. And if we shoot the tank shell, it's going to hit right in the middle. Now, I'm going to ask you a question. Notice how this was an angle of 75 degrees, initial speed of 18 meters per second, mass of 150 kilograms. What would happen if I changed the mass to 500 kilograms? As you can tell, that's extremely heavy. Do you think it's going to fall short of the target or overshoot the target? Think about that for a second, and let's see what happens. Fire. Oh my gosh, it's going straight to the bullseye. All right, the point is mass does not matter. Mass does not matter. It does not affect the rate of fall. It simply does not. And it's hard to believe, but you need to accept it. And I can show you a more mathematical proof for it another time when we get to chapter 5. But for now, it's something you need to accept. Is that mass does not affect the rate of fall. It has absolutely no effect. That's why the 500 kilogram projectile reached the same exact spot that the 150 kilogram projectile reached, precisely because each of them had the same initial speed of 18 meters per second. All that matters in projectile motion is the initial speed. Mass does not. Now let's try some other projectiles just for fun. All right, let's try a bowling ball. And that's 7.3 kilograms. Same initial speed. See what happens. Fire. And it hits again because mass doesn't matter. And we've disregarded air resistance, and so shape doesn't matter either. Now, obviously, in real life, shape plays a role because something bigger is going to have more air resistance, and so that will affect the path. But we're not worrying about that for now. Right now, the main points to remember are what I've said so far about horizontal and vertical components of velocity and path. All right, let's try a pumpkin. Let's try a pumpkin. Fire. Goes up, comes down, smash. Did you see it splat? I remember there used to be a popular band called Smashing Pumpkins. I don't know if you've ever heard of them. Not that it matters, but Smashing Pumpkins was a popular band back in the day. All right, let's look at, oh wow, an adult human. Wonder what's going to happen to him. Fire. There he goes. There he goes. Oh, well, he didn't explode, but I think he's kind of sore. Let's see what else. Oh, we got a piano. Let's try a piano. Fire that piano. Oh, there it goes. Boom. Piano's in a lot of little bits. All right, and finally, let's try a Buick. You obviously can't fit a Buick in a cannon, but this is just for fun. We're going to fire it. 1,000 kilograms, very heavy, but same initial speed of 18 meters per second. And so you should know what's going to happen. We're going to fire it, and it's going to land right on the target and smash into bits. Okay, so the acceleration in projectile motion is independent of the direction of the velocity. So remember that here, if we're just dropping a ball, well, it's certainly accelerating downward, but also the velocity is going downward. So it's accelerating downward, and the velocity is going downward. Here, they just happen to be going in the same direction. But notice here on the right, if we throw this baseball, well, at any particular point along the path, the velocity is tangent to that path, comes straight out of the hands. But during the whole flight, the acceleration is always downward because gravity is always pulling straight down. This is a really neat photo that helps us to understand how the horizontal component of velocity is independent from the vertical component of velocity. So what we have here is a high-speed photo of hundreds of frames per second, and in it we have a ball, a red ball, that is simply being dropped, and we have a yellow ball that is being launched horizontally. And so if you look at the red ball clearly has only vertical velocity and no horizontal component. The yellow ball, however, has both a horizontal component of velocity and a vertical component of velocity, but notice how it drops at exactly the same rate as the red ball. All right, they're following the same distance, as you can see in the lines. At each particular frame, they're lined up just about perfectly. If there's anything short of perfection here, it's just because of, little experimental error. But we can see that they really are lined up and that they're falling at the same rate, even though one has some horizontal velocity and the other doesn't. Okay, so what this means is let's say that you were firing a gun in a vacuum. Well, if you drop the bullet from, let's say, 4 feet above the ground, and then just drop it, it's not loaded, you're just dropping a bullet, well, obviously that'll take a certain amount of time to fall to the ground. But if you fire that same bullet horizontally at 4 feet, it's still going to take the same amount of time to fall. Why? Because the horizontal component of velocity is independent from the vertical component of velocity. Let's look at this problem. Playing shortstop, you pick up a ground ball and throw it to second base. The ball is thrown horizontally with a speed of 22 meters per second directly toward point A. When the ball reaches the second baseman 0.5 seconds later, it is caught at point B. How far were you from the second baseman, and what is the distance of the vertical drop? Now, I'm putting the sketch here as sometimes you'll encounter problems that give you the sketch. Those are certainly easier. But yeah, this is the kind of problem where you actually have to see the sketch to understand the problem. And so what we have here is we have the shortstop throwing, and you can see his initial velocity is completely horizontal, has no vertical. He's throwing it horizontally towards point A. Of course, gravity causes it to drop to point B. All right, so since this is our first projectile motion problem, you'll probably want to just see the walkthrough. If you're ready for a challenge, you could try to do the whole thing on your own. That's fine. But you might want to just see the walkthrough for now. Okay, so we have our sketch. Now let's do our layout. And let's do the ball's horizontal trip first. Whenever you're dealing with projectile motion, which is motion in 2 dimensions, it's horizontal motion and it's vertical motion, it's always a good idea to break it up into parts and do only one direction at a time. So let's do the ball's horizontal trip first. With our layout, we have Vix equals 22 meters per second, t equals 0.45 seconds, and a sub x equals 0 meters per second squared. We need to find s sub x. Quick note on these subscripts. Okay, you're going to be seeing this all year as well. All the subscripts do is they clarify which direction we're talking about. All right, so if we look at Vix, all that means it's still Vi, still initial velocity, but the x means in the x direction, or the horizontal direction. And since this is a purely horizontal velocity, it's just 22 meters per second. The t, of course, is not a vector, it's a scalar, and so it's just 0.45 seconds. A sub x. Okay, this is important also to clarify. With projectile motion, the only acceleration is downward. There is absolutely no horizontal acceleration. If you fire a gun, all right, if you fire a gun, once that bullet leaves the muzzle, there is no more acceleration. The bullet accelerates through the barrel, but once it leaves that barrel, there's no more acceleration. Okay? Same with a pitcher. If a pitcher is doing his windup and throws to the catcher, well, the whole time he's doing his windup, he's accelerating that ball. But once the ball leaves his hands, there is absolutely no more horizontal acceleration. There is only the vertical acceleration due to gravity. Okay, so if we're doing the ball's horizontal trip first, well, then you can see there will be no horizontal acceleration. That's why a sub x, or the acceleration in the horizontal direction, is 0. S sub x, which is the displacement in the horizontal direction, S sub x will be something that we're trying to find. That's why we put the question mark. And based on the layout, we can see that the best equation to use is S equals VIT plus 1/2 AT squared. Again, why the subscripts? All the subscripts do is they clarify which direction we're talking about. S sub x means the horizontal displacement equals VIX, or the horizontal component of velocity, times t, plus 1/2 A sub x, or the horizontal component of acceleration, times t squared. Okay, so now doing our plugging and chugging, we simply put our knowns in and get the unknown. Notice how this AX is just, A sub x is just 0, so that whole term disappears, and we're left with 9.9 meters as the horizontal displacement. Now let's do the ball's vertical drop. The layout would be VIY equals 0 meters per second. T is the same. A sub y is negative 9.81 meters per second squared, and we need to find S sub y. Okay, why is VIY equal to 0? Because since the initial velocity was purely horizontal, the thrower, or the shortstop, did not impart any vertical velocity, either up or down, to the ball. And so, if we're looking only at the vertical drop portion of the trip and disregarding the horizontal portion, we can see that the initial vertical velocity was simply 0 meters per second. Now there is, however, for the vertical portion, a vertical acceleration, and that's due to gravity. That's what's going to cause the drop, and that's negative 9.81 meters per second squared. And we're asked to find the vertical displacement, or S sub y. So we're going to use the same equation, but notice that the subscripts are different to clarify that we're dealing with the vertical drop. And we find the vertical displacement. We have a drop of negative 0.99 meters. And the negative sign just means that it's a drop rather than a rise. Okay, continuing our discussion of projectile motion. This is a layout to kind of put all the principles of projectile motion in one screen. So this is a very important diagram that you want to reflect faithfully in your notes. If we have a vector v sub I, that means the initial velocity. Notice that though this is a parabolic path, the initial velocity has this straight line character, because whatever the projectile is launched from, it's initially launched in a straight line, and that line gets curved, of course, due to gravity. But we're going to look at this as a straight vector vi, straight up from the launch position, and it's launched at an angle theta. The blue dotted line just traces out the path of the projectile. S sub x means the horizontal displacement. S sub y means the vertical displacement. Quick note about S sub y, we're really referring to the vertical displacement during the first half of the trip that I'm tracing now with the mouse arrow. That's going to be a vertical displacement. If we're talking about the overall vertical displacement for this projectile's path, that of course would be 0, because it's returning to the point it started from vertically. But the S sub y here refers to the peak of the path. Alright, then we have a horizontal component of that VI vector, and so we label it VIX, the horizontal component of VI, equals VI cosine theta, and the vertical component, or VIY, equals VI sine theta. Now the vertical component of VI determines how high the projectile goes and how much time it spends in the air. The horizontal component of VI and the time airborne determine how far the projectile goes. So since the horizontal path, or how far it goes, really depends on something that the vertical component of velocity determines, which is the time airborne. With problems like this, it's normally good to do the vertical trip first and then the horizontal. Alright, but definitely write all this down, because these are the nuts and bolts of projectile motion, all on one screen. And you can keep referring back to this as needed while you're still getting used to projectile motion problems. Okay, let's try this final problem. A soccer ball is kicked with a speed of 9.50 meters per second at an angle of 25 degrees above the horizontal. If the ball lands at the same level from which it was kicked, how long was it in the air? how far did it go? Okay, so before you pause the video, just a couple quick points. Remember that you're attacking one unknown at a time, and just do the first question first, which was how long was it in the air, and then worry about the second question. You'll see why. But that's one hint I'm going to give you. The other hint is follow the 3 steps before you do your plugging and chugging, and you should be okay. All right, now I'm going to help you with the sketch only, and then you'll do the rest. This is the sketch to help orient your work. All right, we have our VI, we have our VIY, our VIX, and we have our theta. Okay, so now pause the video, try to figure out the rest of this on your own until you've answered both questions, how long was it in the air and how far did it go, and then resume when you have your answers or if you get stuck. Okay, let's go through the solution. Let's do the vertical trip first. That's usually the best thing to do when you're dealing with projectile motion and there's some kind of launch angle theta involved. When there's just straight vertical motion or just straight horizontal motion, it really doesn't matter. Those are a lot easier. But when you have both, when you have a parabolic path, it's usually best to do the vertical trip first. So the vertical component of VI is VIY, or VI sine theta, and that's 9.50 sine 25 degrees, which equals 4.0149 meters per second. Again, we're not going to round until the end. And so let's do our layout. VFY equals 0. Since there is a final velocity of 0 if we're dealing with the vertical trip. Recall that with this, it's much easier. With this kind of motion, it's much easier to just divide the vertical trip in half and worry only about the upward portion, because we know that on the upward portion the projectile will come to rest, and that's why VFY equals 0. VIY is 4.0149 meters per second, and A sub y, the vertical acceleration, is negative 9.81 meters per second squared, which is due to gravity. So we need t, and the clear choice for our equation is going to be VF equals VI plus AT. Again, with subscripts to clarify that we're dealing with the vertical portion of the trip. And finally, our plugging and chugging gives us t equals 0.409266 seconds, but remember that's just for the first half, only for the first half of the trip. That's how long it takes for the soccer ball to reach its peak, and then of course it has to go back down to where it started, and so you have to multiply by 2. The total time is twice this, so 2t equals 0.82 seconds. So the soccer ball was in the air for 0.82 seconds total. Now let's do the horizontal trip. The horizontal component of VI is VIX, or VI cosine theta. And so we come up with 8.6099 meters per second. Again, we're going to round at the end, not now. And so doing our layout, VIX equals 8.6099 meters per second. T is 0.82 seconds, which we found already. And that's precisely why it's always better to do the vertical component first and then do the horizontal, since the horizontal depends on something we found in the first part, which was t. A sub x is 0 because there is absolutely no horizontal acceleration. The ball gets accelerated while the guy's foot is still in contact with the ball. But once the foot, once the ball leaves his foot, there is absolutely no more horizontal acceleration. Horizontal displacement, S sub x, is what we're trying to find. And so, again, the choice is clear. We're going to use this equation. S equals VIT plus 1/2 AT squared. And then doing our plugging and chugging, we end up with a final horizontal displacement of 7.1 meters. Here's the classwork. Please write these numbers down, and they will be provided as usual on a worksheet. See you in class.